Hey everyone, it's me Hiral Shah, and you all are on my YouTube channel. And hope you all liked my videos and you are subscribed. So previously, in all the sessions, we completed so many methods, right? And lastly, we just completed harmonic functions and the based on harmonic equations, यानी कि Laplace equations and uh, conjugate functions. So, and today's session we are going to conduct one more new method, and it is actually related to limit functions. And in very starting, I think we have started limit methods and examples, right? And at that time, I would say this is actually related to differentiation or continuous functions. So let's start our today's session. I'm starting with the continuity. Uh, I think we before the harmonic functions we did analytic functions and its examples. It means we found analytic functions by using CR conditions, and also we checked the differentiability, right? So in differentiability, I would say one thing that if the analytic functions will be satisfied, if CR conditions will be satisfied, then the function will said to be analytic functions. Now, if the function will be analytic, then it will be differentiable. Now, if the function will be differentiable, then we can say that the given function will be continuous form. Okay, so this one is a channel. If the CR condition satisfied, then it will be analytic. If it will be analytic, then it will be differentiable. And if the function will be differentiable, then we can contribute as an continuous functions. Okay, so same thing we are going to repeat here. Okay, to find the continuity. So our today's session we will study regarding continue. So this concept actually we have studied before our today's sessions. Okay, but the formulas will be changed only. So यहाँ पे सिर्फ आपका formulas ही change होगा, बाकी सब as it is ही है. Okay, so let's start, guys. Here I have written one definition of the continuous. A function w equals to f of z defined in the bounded closed domain D is said to be continuous at a point z equals to z0 of D if limit z tends to z0 f of z exists. Okay, so this is one of the definition of to be continuous, at where the limit will be z tends to z0 form, and when this limit should be exist. Okay, or else we can denote it as limit z tends to z0 f of z equals to f of z0, or else we can denote it as like limit delta z tends to 0 f of z0 plus del z equals to f of 0. So here I have written one notes of its definition only. If f of z is continuous at all the points, agar f of z is continuous, then it is said to be continuous on D. Or here I have written one notes. If f of z is continuous of z, then u and v are separately continuous functions of x and y and vice versa. It means if f of z, yani ki you know that which are the components that will be actually u plus iv form, right? So if u and v, if f of z will be continuous, then u and v will be continuous separately also. Now if u and v will be separately also, then x and y will be continuous also. Why x and y? Because as you know all, by using u plus iv you are finding real and the imaginary parts, and real parts and imaginary part it itself includes x and y components, right? So that's why if u and v will be separately continuous, then definitely x and y will be continuous also. Okay, so this is one of the theory of continuous function, and from this all theory you have to remember this equation, and that we are going to use here. Okay guys, so now let's start with the example. And the question is, determine whether the function f of z is continuous at origin. And where f of z is given x plus y whole square upon x square plus y square, where z does not equals to 0 and the rest of the function is 0, where z equals to 0. So maybe you might be aware, this is a type of question like limit examples. Okay, uh, because in very starting in the analytic functions we did like this kind of functions we have solved, and it was actual a type of limit of examples, right? And at that time I have said one function will be given for z does not equals to 0 or z does not equals to 1 or minus 1 etc. for the numbers, right? This one will be changed, and second one will be 0 for the for that the limit will be into the 0 form, like z equals to 1, z equals to minus 1, minus 2 etc. So here again you have to check, you have to put the limits. So I'm applying limit z tends to z0, and here the point is given. Z0 is one of the point which will be given into the equation. Okay guys. So here you can observe that the z0 is given into the 0 form, right? So in place of z0 we will use now 0. So the limit will be z tends to z0 form. Okay, and f of z, where limit z tends to 0 and f of z equals to, we can denote this function. Okay, now you can see that this one is a z, and that z its limits it's given the limits of z, and here you can observe the function is given into the xy form, right? And so you can't put the limit z directly, so you have to convert that into the xy form, and that is actual not actual x plus iy, right? So here it's includes two components, which is not possible actually. Why? Because here it's given two variables and we can't put two variables limit together. Okay, so definitely you have to convert it into the single form. So for that I'm applying one of the path of y equals to mx, and that this one we have already applied before the before our sessions in the limit examples. Okay, so with the same procedure I'm applying here also. So let I'm applying z tends to 0 along the line, along the path y equals to mx line. So in place of z I'm applying y equals to mx tends to 0. Okay, I'm applying path y equals to mx. So I'm applying mx tends to the 0 form. But as you know all, m is a constant number, right? This is your constant, like 2x tends to 0, then the x tends to 0. So same it is like mx tends to 0, then we can say that the x tends to the 0, right? So here I have written limit x tends to 0, and in place of y now we will put mx. So x plus mx whole square upon x squared plus m square x square. Okay, now from the numerator and denominator the x square will be common, so I'm just taking out, and this one will be cancelled. So the remaining term will be 1 plus m whole square upon 1 plus m square. So now at the last we have to put the limits, but here you can see that there is not available x in the function, right? So of course obviously this one will be your last answer. And as you know all, here you have to bring z equals to 0, because you have applied limit z tends to 0, yani ki this one. So for that you need a function 0, right? And as you can see here, 0 is not coming. So from that we can say that the limit does not exist. Now limit does not exist, it means we can say that the given function is not differentiable, and and so that's why we can say that the given function is not continuous. And this all I have written here. Since the limit depends on m, of course, because we could not remove m from the function, right? So that's why we can say that the limit depends on the m. It takes different values along different path. Thus, the limit does not exist. See, here if we will put some of the values of m, then the path will be changed, right? So that's why I have written here, it takes different values along the different paths. So thus the limit does not exist. And hence we can say that the given function is not continuous. I hope you all understood, guys, because this procedure we have already applied in the limit sessions. Okay. So now let's start with the another one, and the question is given: discuss the continuity of f of z at the origin, where f of z is given z bar upon z, where z does not equals to 0 and 0 for the z equals to 0. So here you can observe that the limit, yani ki the z0 point is given into the 0 form. So again we will apply with the same limit z tends to 0. And here I have put the function z bar upon z. Z bar will be x minus iy and z as it is x plus iy. And again with the same procedure, here it's given two variable x and y, and z having also two variables, so you can't put it directly from applying one of the path of that z. So applying y tends to mx. So again with the same, mx tends to 0, then x goes to 0, and putting the values of z and z bar and the z. So x minus I in place of y, now you have to put mx. So again from the numerator and denominator, the x will be uh, cancel. So the remaining term will be 1 minus im upon 1 plus im. And again you are getting the term that having not x. So you can't put the limits of x. So this one will be non-zero term, and so that this function is for this function we can say that the limit does not exist, and so that's why the given function yani ki f of z is not continuous at the given point. Now let's start with the third one example, and the question is given: show that f of z equals to real parts of z square upon mod z, where z does not equals to 0 and 0 for the z equals to 0, is continuous at z equals to 0. So here it's already given that you have to show the given function is continuous. So maybe the in the end the answer will might become 0, then only then it will be continuous. So whatever it is coming, whatever it will become, we are just going through our method. So here you can see that the limit is given 0 form. So the function's limit will be actual again 0 as z tends to 0 form. In place of z0 we will write 0. So limit z tends to 0 f of z equals to limit z tends to 0, and here you have to put the function of f of z, and it is given real number of z square upon mod z. So real parts of z square yani ki x plus iy whole square, as we know all the values of z, and into the denominator we can write mod x plus iy, or else directly we can write under root of x square plus y square. And now here you can see that limit z tends to 0, and real parts of here I have just open the brackets, and it will be x square plus 2x iy minus I plus I square y square, and the values of I square will be minus 1, so that's why it will be minus y square. So I'm just separating the terms real and the imaginary parts. So this one will be your real part. So I have written together x square minus y square plus 2ixy. This is your imaginary part. And as I said in our last slide, in place of mod z, you can also write under root of x square plus y square. So that's why I have written under root x square plus y square. And this is in the numerator you can see that here it's written the real part. So real parts of this both will be, see, this is your imaginary parts, okay? So which one will be your real parts? It will be x square minus y square. So only term remaining will x square minus y square upon under root x square plus y square. Okay, now with the same procedure, this function having again two variables. So this for the z function we have to apply one of the path of y tends to mx. So I'm applying. So in place of y we will put now m square x square, yani ki mx, and the limit goes to x tends to 0 form. So x square minus y square yani ki m square x square upon under root of x square plus y square yani ki m square x square. And now here you can see that from numerator x square will be common and from the denominator x will be common, right? Because here it's given a root of the whole function. So if we will write out of the root, then it will be x sum only. And the remaining term I have written here, that 1 minus x square upon under root of 1 plus x square. And from this both this x will be removed, right? So the remaining term will be now, yes, just a second guys. Okay, so the remaining term will be now x into the 1 minus x square upon under root of 1 plus x square. As you can see that here it's given the limits of x, so putting 0 in place of x, so it will be 0. And as you are getting, limit is not depends on the m, right? Because here you are not getting m, so definitely we can say that the limit is not depends on the m. So it means it is independent of the path. So that's why we can say that the limit exists, and if limit exists then we can say that the given function will be differentiable, and that's why we can call as it is continuous also. So that's why I have written hence the f of z is continuous at the point z equals to 0. So these all are very easiest examples, and I think I'm going to complete this topic. And now in the next session, we will start with one more new method, and I think we are just going end of this analytic functions. So now it's remaining only one or two methods. Okay, so till that please do the practice of this all the examples. Thank you guys.